Hi everyone, today we're talking about polynomial models and rational models. So we're going to first start off with polynomial models. So we have seen linear models and we've seen quadratic models already, but what happens if you have like a cubic function or a quartic function or even a rational, something like with a variable in the denominator of a fraction? To begin, we've got cubic functions. So it's a function with the largest power of x, that's 3. So you look at the degree technically of the function. So when you see that 3, it's the biggest exponent in that whole function, you know it's cubic. If you had a 4 as the biggest power, then that would be quartic. And anything past quartic, we just call a 5th degree polynomial or 6th degree polynomial. Math studies right now just stops at quartic, just so you're aware. For all of these functions, you have two examples of cubic function graphs that I gave you. They look similar. They have, they both rise eventually to the right, and they both come from negative y values to the left. You can have a few extra bumps in these polynomial functions, but we pretty much keep it pretty light, and most of our math is done in our graphing calculator, but you can do the same in Desmos if you don't have your graphing calculator. So you want to pause this and go get your graphing calculator if you need it, or bring up Desmos. Your domain is all real numbers, so you can plug in any x value that you want into these functions, and they will be defined. For example 1, we have a fish problem. So the number of fish, F, in a pond from the period of 1995 to 2010 is modeled by this formula. Now, we know X is the number of years after 1995. I'm going to show you how to use your graphing calculator to sketch this function. All right, so they will usually tell you to fix your window. So they say use the graphing calculator to sketch the function for the range of x values from 0 to 18. I will show you when you need to know that. So first step, you're going to grab your graphing calculator, you're going to hit y equals, and it's going to pop up in y1, that's your first equation. If you have to enter more equations, you'll enter into y2 or y3, of course, but right now just y1. Drop in that whole entire function. Make sure you use the little caret button to get to the third power. And once you have everything in there, you need to fix your window. That's your viewing window for the function. So if you just go and hit the graph button, you might not even see all of your graph. All right, so for this problem, they told me to fix my window for my x values. So my x minimum would be the lowest number, 0, and what x max is all the way over to 18. So that's going to change your x-axis from 0 to 18. And then you need to be smart about the y min and y max. I put my y min as 0. And I took a look at my function and I said, well, how high is my function going? Look at your constant at the end, okay? So that number is 67. That's actually your y-intercept. So you know the graph is likely going to be above that, all right? So I literally chose. You could make it 100, you could make it 95. It doesn't matter. You just have to get over 67, all right? So I went from 0 to 90, and that gave me an accurate description of my graph here. And there you go. So make sure you can enter all of that because we're going to use this graph. You can find the number of fish in the pond after 6 years. Now, you can do this by hand, of course, and I showed you the math behind doing it by hand. We're going to use x as 6 because our x's are our number of fish. And you literally just plug it into the equation and you get 50.08 fish after 6 years. And there's another example of that in C. Find the number of fish in the pond after 13 years. You're just plugging in x equals 13 into your function and you get 56.73 fish after 13 years. All right, or you can be smart. We can use our table in our graphing calculator. Look, it's giving you a whole t-chart for whatever x value you want. They used our x minimums from 0 to 10, and they showed us that. But if you scroll down, okay, hold on. To get to the table, you want to hit the second button and then hit the graph, and you'll see the table directions are right above the graph button. So hit second, graph, to get to your table. And then you're going to scroll down until you see x equals 6, and you get your y value of 50.08, which we did by hand not too long ago right there in part B. And then for x equals 13, you can scroll down a little bit more and you'll see 56.73. So do you have to do that by hand? Of course not. Use your table. Be smart, work less. For our next example, we have a pandemic that's modeled using the equation of y equals x minus 20 to the third plus 5,000, where x is the number of weeks after the outbreak started and y is the number of cases reported. Use your graphing calculator to sketch the function. All right. Now they tell us, again, our x values. So we're going to fix our window according to that. You're going to enter your equation into y equals, type it all in, and then fix your window. So I did, let me get my x min because they told me I wanted my lower boundary to be 0 and 30 to be my max. So that will label my x min 0 to 30. And then I had to choose my y min and y max. So I chose it at 0 because that kind of logically makes sense for a pandemic, right? And then I looked at my formula and I saw 5,000 as my y-intercept. So I need to go well above that 5,000. So I chose 10,000 all the way up here. All right, and if you enter all that, you should get the same graph as I do, maybe just not in color. And our next couple of questions, we want to find the number of cases after 10 weeks. So I go to my table, I hit second, graph to get to my table, and you'll see I scroll down until I saw my x value of 10, and its corresponding y value is 4,000. So you can do that by hand, plugging in x equals 10 into the function. Just be careful. So we see that 4,000 cases occurred after 10 weeks. And then I scrolled more down to tackle part C, find the number of cases after 20 weeks. I just scrolled down until I saw x is equal to 20, and that was 5,000 cases after 20 weeks. Now, is this a good model to represent the number of cases of a pandemic? Take a look at this graph. Does that look like our pandemic right now, right? I have a problem over here. So it was increasing, right? And then your graph started to plateau. Ideally, that's what you want in a pandemic. But then your number of cases started to rise after this x value. All right, so I would say this is not a good representation for a pandemic because after 20 weeks, the cases kept rising. Now we get into rational functions, which are also called reciprocal functions. You've seen these in Algebra 2. Just a quick refresher. You've got what we call branches. Branches are the blue pieces of the graph, and then your actual function is f of x is equal to 1 over x for this particular graph, and we have a domain restriction of x can't equal 0, and that's because you have a fraction and you can't have a 0 in the denominator and expect that function to be to exist actually. So it's undefined when x is equal to 0, which in turn creates this vertical asymptote right here, where your graph is never going to touch that vertical asymptote, but it gets really close to. So it kind of skims along the vertical asymptote, but will never cross it. And you'll see that you actually also have a horizontal asymptote of y equals 0, or what we call the x-axis. So again, your branches are getting really close to these asymptotes, but will never cross them. All right, another example of a rational function looks like this. So these are little arrowheads up here and down here. So this one is when y is equal to 1 over x squared, which again, same story, x can't equal 0, which creates a vertical asymptote at x is equal, So your function is not defined when x is equal to 0. So vertical asymptote, x is equal to 0. And you also have a horizontal asymptote along this x-axis, or y is equal to 0 for your horizontal asymptote. All right, and you get 2 branches. Here's an application of our rational functions. We have a rectangle that has an area of 1.5 meters squared. Let the length of the rectangle be y and the width be x. Okay, we want to show that y is equal to 1.5 over x. Now, I look at this problem and I say, what? And I go, well, what do I have? I have a rectangle and they're telling me area is 1.5 meters squared. So I think back to, well, I know the area of a rectangle is just area is equal to length times width, right? And they're telling me call x the width and y the length. All right, so I went from my good old area is equal to length times width and replaced it with x times y is equal to my area. And then I'm able to plug in, they told me area is equal to 1.5 in my problem, so I dropped that in, and then I just divided by x both sides, and I got y equals 1.5 over x, which is actually a rational function. Now, that's as long as x can't equal 0, or you don't have an area of the rectangle. Okay, use your graphing calculator to draw the graph. So they told me my x min and my x max. So I plugged that in for my window, and then I adjusted my y value until I found my graph, or at least enough of the graph. So my x values go from 0 to 10, and then my y values, I included some negative to see if it would cross over that x-axis, all the way up to 15. And of course, the graph is not showing the arrowheads on the branches, but make sure you understand that they do go on forever. So what happens as the x values get closer to 0? So we're looking here. When you have x values that are really close to 0, what is happening to your corresponding y values? Your y's are really big, right? So I would say as your x values approach 0, the y values are getting really big, or a large positive number they're approaching. On the next problem, part D, what happens as x gets closer to 10? So as your x values increase to 10, what's happening to your corresponding y values? They're really small, right? So I would say as your x goes towards 10, the y values get really small or approach 0. All right, and one more question. Write down the equations of the vertical asymptotes and the horizontal asymptote. So our horizontal asymptote is y is equal to 0, horizontal, and your vertical asymptote is that y-axis, which is the equation x is equal to 0 for your vertical asymptote. So I wrote that down below. for you. All right. Well, that completes that lesson. I hope you are all well